Hi, today we're going to look at an intriguing integral. It's the integral from 0 to 3000 of x squared minus the floor of x times the ceiling of x dx. Before we jump into it, let's look at a few definitions and examples of what the floor and ceiling functions are like, how they behave. The floor of some real number x tells us that we're going to take the maximum integer m that's less than or equal to that number x. So in other words, the floor of x tells us to round down to the nearest integer. As an example, the floor of 2.6, that rounds down to 2. And for the ceiling function, the ceiling of some real number x tells us to take the minimum integer n that's greater than or equal to our number x. In other words, the ceiling of x tells us to round up to the nearest integer. So for example, the ceiling of 5.1, that rounds up to the integer 6. Okay, so we know how these two functions behave. So let's start looking at our integral. For reference, let's call this integral I. Well, the real issue is going to be with these floor and ceiling functions. How exactly do we handle them? Well, first of all, we can split this up as the integral from 0 to 3000 of x squared dx minus the integral from 0 to 3000 of the floor of x times the ceiling of x. However, what we're going to do is find a closed form formula for the following integral instead. We'll call this I of n, or I sub n, and we'll go from 0 to n of x squared dx minus the integral from 0 to n of the floor of x times the ceiling of x. Now, why are we doing this? Why are we changing that upper bound to n? Well, we're going to look at how these two functions behave, and we're going to generate a nice pattern. And like we said, that will help us find a closed formula for this expression here. So notice the following. Let's take some half-open intervals and see how the floor and ceiling functions behave. In the interval from 0 to 1, so including 0 but not 1, the floor of any number between these two integers will always round down to 0. So for example, if we had 0.1, 0.4, 0.88, those are values between 0 and 1, and they'll always round down to 0. And the ceiling of any number between these two integers will always round up to 1. Well, how about in the interval 1 to 2, this half-open interval, including 1 but not 2? Well, any number in here, let's say 1.5, 1.7, etc., the floor of any one of those numbers will round down to 1, but the ceiling of any of those numbers will round up to 2. And we could continue on, look at the half-open interval from 2 to 3, 3 to 4, 4 to 5. In general, if we look at the half-open interval from n minus 1 up to n, well, how do our floor and ceiling functions behave? The floor of any number between these two integers will round down to n minus 1. And the ceiling of any number between these two integers will always round up to n. So what does this tell us about our integral over here? Well, I sub n will be the integral from 0 to n of x squared dx minus, well, as we work our way from 0 all the way up to n, we'll look at the integral from 0 to 1, then the integral from 1 to 2, then the integral from 2 to 3, etc., until we get to the integral from n minus 1 to n. And what do those integrals look like? Well, we'll have, like we said, the integral from 0 to 1 of the floor of x times the ceiling of x dx, plus the integral from 1 to 2 of the floor of x times the ceiling of x, plus all the way up to the integral from this last interval, n minus 1 to n, of the floor of x times the ceiling of x dx, and so what does that look like? I of n is this integral here minus, well, in the interval from 0 to 1, this interval here, the floor of x is 0, the ceiling of x is 1. So we have the integral from 0 to 1 of 0 times 1 dx. Plus, how about in the interval from 1 to 2? Well, from 1 to 2, the floor of x is 1, the ceiling of x is 2. So we have 1 times 2 dx. And when we finally get all the way to our integral from n minus 1 to n, this interval here, the floor of x is n minus 1 and the ceiling of x is n. So we have n minus 1 times n dx. Okay, perfect. Now what? Well, we can compactify all this into a nice summation. So what we end up with now is I sub n as being the integral from 0 to n of x squared dx minus the sum of, well, the sum of what? A whole bunch of integrals. And let's say we start our counter at k equals 1. And we write this lower bound as k minus 1. So as we begin adding up our integrals, with k starting at 1, this lower bound will be 1 minus 1 or 0, up to k. And we're going to add all the way up until we hit n. And what's in our integrand? Well, we have k minus 1 times k dx. Again, when our counter starts at 1, this gives us 0 times 1. And then when the counter hits 2, we have 1 times 2. Exactly what we have here, and so on. Great, so now we have this. So we'll make some more room, and we'll come right back. Okay, so we're back. We left off here with our integral I sub n being equal to this here minus this sum of those integrals there. Well, this integration is quite straightforward. K minus 1 times k is just really a constant term. So integrating this will just give us k minus 1 times k times x, and we'll evaluate it from k minus 1 to k. And we can carry out this integration very easily as well. That's a simple polynomial. So integrating this, we get 1/3 x cubed evaluated from 0 to n minus the sum from k equals 1 to n of, like we said, k minus 1 times kx evaluated from k minus 1 to k. Okay, good. So now we have I sub n equals, all right, well we have 1/3 of, our upper bound gives us n cubed, minus, subbing in our lower bound gives us 0 cubed, minus the sum from k equals 1 to n of k minus 1 times k times, now for x, we'll put in our upper bound minus our lower bound. So we have k minus 1. But this is nothing more than, well, n cubed minus 0 cubed is n cubed. So we have 1/3 n cubed minus the sum from k equals 1 to n of k minus 1 times k times k minus k is nothing, minus 1 is 1. So we're left with just 1. Okay, good. So this gives us the following. I sub n equals 1/3 n cubed minus the sum from k equals 1 to n of, let's distribute the k here, k squared minus k. Well, if we do that, now we have two summations to work with. So we have minus the sum from k equals 1 to n of k squared minus the sum from k equals 1 to n of k. Okay, that's great. Now here we obtain the following. I sub n equals 1/3 n cubed minus this summation plus this summation. Well, this summation right here is just the sum of the first n squares. And there's a well-known closed formula for that. And it's nothing more than the following. N times n plus 1 times 2n plus 1, all divided by 6. And for the next summation, that's the sum of the first n positive integers. And there's also a well-known summation for that. That's nothing more than n times n plus 1 divided by 2. Well, where does this take us? We have I sub n equals 1/3 n cubed minus, well, let's distribute everything here in the numerator. We have n squared plus n, and that will be multiplied by 2n plus 1, all divided by 6. And then over here, just to give us a denominator of 6 as well, we'll make this a 6, and we'll make this a 3. So distributing in the top gives us 3n squared plus 3n. And now we'll carry on. We'll distribute here again, and then combine these two fractions, simplify everything, and see where that takes us. So stay tuned. Okay, so here we are now. We left off with I sub n equals 1/3 n cubed minus this fraction plus this one. Let's expand the numerator here. So that gives us I sub n equals 1/3 n cubed minus 2n cubed plus n squared plus 2n squared, so that's plus 3n squared plus n. This is all divided by 6 plus the last fraction. Okay, well, let's combine these two fractions with that denominator of 6. And we could even do the same with this one. We can simply make this a 6 and this a 2. So we have the following. 2n cubed plus 3n squared plus 3n minus 2n cubed minus 3n squared minus n, all divided by 6. And so I sub n is now what? 2n cubed minus 2n cubed, those cancel out. Then we have 3n squared minus 3n squared, those cancel out. And then we have 3n minus n is 2n, and divided by 6. But that just reduces to 1/3 of n. Now remember, we had taken our integral here and written it as I sub n equals the integral from 0 to n of x squared minus the floor of x times the ceiling of x dx. And so our n was simply 3,000. So what does that tell us then? Our I sub n, our integral evaluated at n equal 3,000, is simply 1/3 of 3,000, which is 1,000. And that completes our integral. So the integral from 0 to 3,000 of x squared minus the floor of x times the ceiling of x dx is 1,000. Thanks for watching.